Let me introduce our paper, Vibration Vanquished, Enhancing Grasping of Deformable Objects with Jet Gripper Technology, the aim of which was to ensure the stability of holding deformable objects during grasping and manipulation using a jet grippers. To begin with, let's understand what jet grippers are. According to standard classifications, we often won't even encounter this type of end effectors. We will only see the general name pneumatic grippers or suction cups. Additionally, in other classifications, we can find a distinction between suction cups and Bernoulli grippers. Therefore, in previous studies, we have made a systematic review of pneumatic gripping devices for industrial robots, where we see a clear separation of airflow and airjet as the main types of pneumatic grippers. According to the method of using a compressed air jet, there are 4 types of these grippers. Let's take a closer look at them. So the first type is a nozzle grippers with a developed end surface, often called a Bernoulli grippers with a cylindrical nozzle. The second type of grippers is an ejection nozzle, which ejects air through a radial nozzle, resulting in negative pressure in the center of the gripper and positive pressure at the edges. This grippers, like the previous one, is often called a Bernoulli gripper because the Bernoulli equation for fluid dynamics is used to calculate its lift force. Next type is the vortex gripper, which creates negative pressure in the center of the gripper by rotating the airflow using tangentially placed nozzles. The last type are the supporting grippers, which use a jet of compressed air to lift the object by creating an air cushion underneath them. Due to the effect of pneumatic levitation and low-contact grasping, jet grippers have significant advantages over other types of pneumatic grippers. Among them is the ability to hold fragile, deformed, with holes, porous, and objects of various roughness. We have developed a gripping device for textile objects based on a jet ejection technology. A grid is added to the design to prevent the interaction of the ejecting airflow with the object in the gripper area. As can be seen, compared to a classic vacuum suction cup, we have achieved 100% success in grasping deformable objects, especially porous ones. We also conducted a study of the influence of input parameters on the force characteristics of the gripper, proposed a finite element method for modeling the grasping process, and substantiated a method for rapid prototyping using 3D printing. Speaking about the modeling of the grasping process, it should be noted that it is very difficult to simulate the behavior of porous textiles of various weaving methods. Therefore, it was proposed to use a simplified method by connecting a tube of a certain length and diameter to simulate the porosity of the object. By increasing the length of the tube, it is possible to increase the friction force and reduce the amount of air passing through the simulation system. As a result, it was possible to predict the lifting force of the gripping device with an average error of 13%. Let's talk about motivation. A large number of automated lines in the textile industry easily handle large deformable objects through the use of conveyor lines. However, when it comes to objects that have been cut or are smaller, human resources are used everywhere for grasping and manipulation. The same applies to processes after cutting by other methods. There are many types of grasping systems for deformable objects, but they have a number of disadvantages, including significant energy consumption, problems with gripping objects that have taken the shape of the object on which they lie, and adaptation to objects with different orientations and positions in space. Of course, there are combined grippers, for example, jet with needle. Its advantages are that it is a local gripper that can lift the object and then pierce it with needles to fix it. However, this technology is only applicable to certain types of products, as it damages the object. No one wants a t-shirt with holes. Since the grasping is only the initial stage, we conducted a study of the effect of changing the orientation of the gripper on the holding force of deformable objects. We found a positive effect in increasing the holding force with increasing orientation due to the friction force. Also, during the study on the implementation of dexterous lifting of a deformable object, we found a significant effect of object vibration on the stability of holding. If complex grasping systems are used, vibration can be transmitted from the robot to the end effector to the object very easily. However, this is usually the vibration of the motors, which can be compensated by an improved method of actuator control. In the case of local grasping systems, additional vibrations of the deformable objects arise due to the interaction with the airflows created by the grippers and the movement of the object. Considering the grasping or holding process, we will see that the outgoing air outside the grid will create oscillations of the deformable object, causing vibration. During manipulation, the same airflows affect the oscillations, which in turn leads to loss of contact with the deformable object. To determine vibration, we developed an experimental setup, the main component of which is piezoelectric sensors that sense the vibrations of a deformable object while it is held by a gripper and at different supply pressures. It is clear from the studies that depending on the amount of material hanging outside the gripper, different vibration frequencies will be achieved. The same applies to whether the sagging occurs on one side or on both sides simultaneously. Therefore, two measurement schemes are proposed, varying the sagging on one side and on both sides evenly. To solve the problem with vibration, it was proposed to improve the design of the anti-vibration grid and redirect the airflow in the opposite direction from the direction of the working surface of the gripper. For this, a rounding was added to the design of the anti-vibration grid, characterized by two parameters of the height h2 and the beginning of the rounding from the edge of the grid M. For the experiments, the material, thin cotton, was selected, which has the greatest vibration problems among all the studied materials presented in the project. We can see the results of the vibration. The investigated deformable material at the gripper supply pressure of 200, 300, and 400 kilopascal. The first column reports the experiment with the material sagging from one side. Accordingly, the second column reports the experiment with the material sagging evenly from both sides. Each row corresponds to a gripper with certain parameters of the anti-vibration grid. The first row, H2, is equal to 0 and is the previously proposed gripper. The second row, H2, is equal to 1 millimeter. The third, H2, is equal to 2 millimeters. For H2 greater than 3 millimeters, the experiment showed the absence of vibration, so the data are not given. From the results obtained, it is obvious that when sagging from two sides simultaneously, there will be less vibration of the material due to the need for the airflow to lift a larger mass of sagging material. The most important result is that with increasing the height of the anti-vibration grid rounding, the vibration gradually disappears, first for lower supply pressures and then for higher ones. To ensure the adequacy of the finite element modeling results, in the case of rounding the anti-vibration grid, it is necessary to make changes to the computational mesh, as well as to the initial parameters of the system. This will allow us to obtain both a simulation of flows that coincide with the experiment and the force parameters of the modified gripper. By changing the parameters of the rounding height, the anti-vibration grid H2, and the start of the rounding M, we obtained the distribution of the lifting force for the supply pressure, 200, 300, and 400 kilopascal. We see that the maximum force values can be achieved for H2 equal to 1 millimeter. But from the point of view of avoiding vibration, we cannot choose this option. Instead, through experimental studies and modeling, we determined that H2 equal to 5 millimeters will be sufficient to perpendicularly redirect the airflow in the opposite direction from the grasping surface. When H2 is increased beyond 5 millimeters, the lifting force in all ranges will decrease due to interaction with the grasping system elements. Such parameters of the anti-vibration grid design completely eliminate the vibration of the deformable material during holding for all supply pressure ranges. Since vibration was overcome for the most demanding of the studied material, this is fully true for all other materials studied in the project. From the results obtained, the lifting force will change sharply for the gripper at H2 equal to 5 millimeters, depending on the parameters of the supply pressure and the start of rounding M. Therefore, to determine the optimal parameters, the support vector regression machine learning method was used, which gave us an accuracy of 99.74%. We see that depending on the operating range of the supply pressure, the optimal parameters will differ. However, the most effective in the average overall studied ranges of supply pressure, M will be equal to 14 millimeters. In conclusion, we would like to highlight the most important thing. First, the parameters of the grasping system were determined, which allowed to complete vanquishing of vibration when grasping deformable objects. Second, the optimal parameters of the anti-vibration grid were determined, which allowed to increase the lifting force by 53% on average compared to the previously proposed gripper. Thanks to the use of the proposed gripper and the new dexterous lifting method of deformable objects in our next paper, we managed to reduce the energy costs for lifting from 16 to 78%, depending on the type of material. Stay tuned. Taking this opportunity, we would also like to invite all interested parties to submit papers to the special issue Advanced Grasping and Motion Control Solutions, Edition 2 in Robotics. Thanks for your attention. If you have any questions or suggestions for cooperation, please contact the corresponding author.